Okay, I'm back with the third and final part of pharmacodynamics. In the first two segments, I spent a lot of time using words and still images to explain ligand-receptor interactions. Now I'm going to use a series of animations to try to give this dynamic process some life. For each example in this series, you'll see a set of 8 receptors in a row like these, and their effectors right below them. The key on the bottom shows you that when a receptor is in an inactive conformation and is colored a light yellow, then its bottom end does not push on the effector. So the effector is also inactive, indicated by a light beige color. When the receptor gets activated, indicated by turning a darker brown color, then its bottom end does bulge out and stimulates the effector, which turns red to show that it's been activated. Even this first baseline animation shows us something new. Although there are no ligands present here at all, you can see that receptors still activate their effectors occasionally, exhibiting apparently random spontaneous activity at a pretty low level, which is the way things often happen in real life. Now that we understand the basic setup for the animations, let's add a ligand and see what happens. The first ligand I'm showing in this system, colored light blue, is a high affinity full agonist present at a concentration equal to its Kd. This ligand is shaped to fit very nicely into the receptor binding site, which is why it's a full agonist. There are several things to notice here. First, try to look at the whole set of receptors all at once. You'll see that over time, the average number of activated receptors at any instant is about 4 out of 8, about 50%. Sometimes there are more, and sometimes there are fewer. But the point is that in a dynamic system, things are constantly changing. And when we talk about the effectors being 50% activated, that's an average number that bounces around over time within a modest range because of biological noise. Now focus in on an individual receptor and watch what happens when a ligand molecule binds to it. Because this ligand binds so tightly, with such a high affinity, once it gets into the binding site, it stays there for a good long while before it dissociates. When we look at a low affinity ligand later, you'll see that that kind of molecule behaves quite differently. Finally, focus on the receptors and effectors together, and notice that virtually every time a receptor is activated by this ligand, the effector associated with it lights up and activates too. This pattern is characteristic of a ligand with high intrinsic activity, which is why I'm calling this a full agonist. Over on the right is a dose-response curve, where we can see how this scenario would be plotted. Since we've got about half of the receptors occupied at any instant, we see about half of maximal response. So that's all good. Let's next see what this looks like if we use the same ligand, but we just go to a higher concentration. We're back with the same light blue ligand, now at a concentration much higher than the Kd. Basically, everything's the same as last time, except that now there are so many ligand molecules around that whenever a receptor binding site opens up, one of the ligand molecules finds it quickly. As a result, at any instant in time, about 7 out of the 8 receptor molecules are activated, and so are their effectors. The dose-response curve shows where we are too, getting close to the saturation point. I think that we understand this light blue ligand pretty well, so let's make things more interesting by looking at a different ligand. This dark green ligand is new. It looks a lot like the light blue one, but the dark green ligand is slightly rounder at the top, and although it fits pretty well into the binding site, it's not as perfect a fit as the light blue ligand was. If you focus on one receptor for a while, you'll see that when this ligand binds, it doesn't stay bound nearly as long as the first ligand did. That explains why, even though the concentration of the dark green ligand is just as high as the animation we just saw, in this case, only about 50% of effectors are bound at any instant, while almost 90% of the receptors were bound with light blue ligand at the same concentration. This dark green ligand clearly has a lower affinity than the light blue ligand did, and that's consistent with its dose-response curve being further right on the graph. In spite of it having lower affinity, though, it still activates effector very efficiently, and its dose-response curve does eventually climb up to 100% of possible response. So we can be comfortable calling this a low affinity, but still full agonist. Here's a third kind of ligand, a light green colored one that's labeled as a high affinity partial agonist. This guy is shaped at the top exactly like our first ligand, the high affinity full agonist, but it has a shorter stem, which means that it's not so certain to poke the effector in a productive way when it binds to the receptor. This is actually a pretty interesting situation because at this high concentration, the receptor is almost fully occupied almost all the time, consistent with this ligand having a high affinity. But you can easily see that there are lots of times when the ligand binds without causing the receptor to activate the effector, meaning that it has low intrinsic activity. And this is the reason that it's a partial and not a full agonist. All of this is reflected on the dose-response curve by the fact that the curve for this drug plateaus well below 100% of maximum possible effect. Up to this point, the animations have just reiterated things that we already saw before, but now comes something new. This dark blue ligand has a shape that nicely fits the receptor binding site, but it has no effector stimulation stem at all. So when given by itself, it seems to do absolutely nothing. Then why did I label it as a competitive antagonist? Because when this ligand is present, it can profoundly affect the action of other ligands and influence biological response that way. Here's that same dark blue ligand along with the first ligand that we saw, the light blue, high affinity, full agonist, with that agonist being present at a concentration equal to its KD, just like in the first animation. Watch what happens at the binding sites. You'll see lots of times when the dark blue ligand is sitting in the binding site, and then a light blue ligand tries to bind there, but it can't because it's being blocked by the dark blue ligand. As a result, even though we have the light blue agonist present at its KD concentration, we're getting less than 50% of maximum effect. You can imagine that if the light blue agonist was an endogenous neurotransmitter, Then, by adding the dark blue ligand, we would effectively decrease signaling by the neurotransmitter by competing with it for receptor binding. That's why we call this kind of ligand a competitive antagonist. The last animation shows another kind of antagonist. This black ligand looks like the competitive antagonist and has the shape to fit the receptor binding site, but it also has some spiky things on it that represent reactive chemical features. When this ligand binds to the receptor, the reactive chemical features form permanent covalent bonds with the receptor. As a result, the black ligands permanently block the receptors where they landed, and when we subsequently add agonist, no matter how high a concentration of the agonist that we use, we can't overcome the block and can only activate the receptors that were untouched by the black ligand. We call this a non-competitive antagonist, and it has the effect of making the dose-response curve for the full agonist look like it's only a partial agonist. Here's the sample question that I showed at the start of pharmacodynamics. Hopefully, I've explained the concepts well enough that you can answer it now. I'll post it online with a couple of others for you to chew on as well. Because of time, that's going to be the end of material for Unit 1 that will be on exam number 1. I'll add the rest of the topics that I mentioned because you do need to know about them, but you won't be responsible for them yet. So good luck with the exam.